All right, so let's start. Welcome back, everyone. Hello. Hello, Elizabeth. So to start with, we are going to have a first talk on high-dimensional dynamics of SGD for Gaussian mixtures by Elizabeth Collins-Woodfin from McGill. Please go ahead.
Thank you very much to the organizers and to all of you for being here. This has been a really exciting conference so far, and I look forward to more talks later today and tomorrow. So I think in the original title that I submitted, it was advertised that I would talk about both GLMs and Gaussian mixture models. And for the sake of time, I've decided to focus on this Gaussian mixture setting. But if you're interested, I'm happy to talk to you about our previous paper, which does include both single index models and multi-index models. So this one is based on joint work that's in progress with Invar Sarusi, and the previous paper that I mentioned is joint with Invar Sarusi as well as Courtney Paquette and Elliot Paquette. All right, so the goal of the work that I'll be discussing today is to understand the high-dimensional dynamics of SGD for Gaussian mixtures, and specifically with an emphasis on non-isotropic data. There's been a variety of previous work in this area. This is certainly not an exhaustive list, but I wanted to at least mention two important works that are related to what we're doing. And the methods that I'll be discussing today build on this previous paper that we did, which was focusing on GLMs. So what we're doing here is extending it to the case of Gaussian mixtures. So I'll begin with just the setup for Gaussian mixture models, and I'll go in some detail with a simple example of binary logistic regression. And even in this simple setting, you can kind of see the effect of how non-isotropic data behaves with SGD in this setting. And then I'll talk a little bit about the methods that we use for our proofs, and as well as some other examples and extensions. So just to begin with the setup, we'll be looking at Gaussian mixtures. So here we have this labeled data. A will be the data point, and then Y is its label. A is in dimension D, and we're going to take D to be very large. In fact, we're going to be taking a limit as D goes to infinity. Y will be in dimension L, and L we will take for the moment to be fixed. Then the L represents also the number of classes from which the data is coming. So in this simple picture that you see right here, L would be 2. So you see there's these 2 Gaussian clusters that the data are coming from. And we say that there could be potentially different probabilities of coming from each of the classes. So we denote by PI the probability that the data came from class I. So here's class 1, here's class 2. And then conditioned on whichever class it came from, the data will be distributed as Gaussian with some mean and some covariance. And the label, there are other possibilities, but we'll begin just with the simple setting where this is a one-hot label. So it's just going to be a vector with a 1 in the entry corresponding to the class from which it came. All right, and so then we have associated with this an optimization problem where we're trying to minimize some risk function, which is given as the expectation of some function. And this is similar to the settings that we've seen in a lot of the previous talks, where everything is kind of coming in the form of the parameters that we're trying to optimize taken as an inner product with the data vector. And here we have some assumption on the functions being locally Lipschitz. All right, and so then the way that we're optimizing this is via streaming SGD, and so, or online SGD, if you like. We're taking one data point at each iteration, and the number of samples that we take will be proportional to the dimension of the data. And so eventually, both this N and this D will be going to infinity. And then at each iteration, basically what's happening is an index is going to be chosen at random. This represents like which cluster is the data coming from. And so I is chosen with probability p sub I. And then based on that, we have this distribution of the data that I had discussed before, which is going to be Gaussian with some mean, course, and some covariance based on the class. And then finally, we have our SGD step. And so we have here the gradient. We're taking the step size, gamma is representing the step size, and we're scaling it like 1 over d. So these step sizes are smaller when the dimension is large. And this turns out to be the correct scaling in which you get interesting limiting behavior. And then our gradient. Okay. And so as I said, we're focusing on this high dimensional limit where n and d are going to infinity in a proportional manner. And we want to look at what is happening with the risk curve as well as other statistics that we can handle. Now, in order for this limit to actually make sense, we need this the sequence of the means and the covariances to behave in some appropriate manner. And so the key assumption is basically that the operator norm of the covariance matrix on each of the classes should be bounded independent of d, and that this should be, converging to some constant in the limit. And likewise, also the normalized trace should be converging to some limit. And that's just, otherwise the limit statement doesn't really make sense. For reasons of the proof, we're going to assume that these covariance matrices commute with each other. It's not clear to me at this moment whether this is really an essential assumption for the result to hold, but it certainly dramatically simplifies the proofs, as we will see later. And then finally, I'll mention that I'm going to kind of assume throughout the talk that the number of classes is just some fixed finite number, but we can actually allow it to grow very slowly on the order of log of d. All right, so the main result that we get is something of this form. So we're going to look at this L, which is the risk that we're interested in, evaluated at X, which is the SGD parameters. And we're going to compare it to some deterministic quantity, which will be this curly L. And what we will show is that as d, the dimension, goes to infinity, that this is going to concentrate. Okay, so I'll say something now about the scaling. So we're going up to some time capital T, and T is the ratio of the number of samples to the dimension. So I said these were going to be proportional, so capital T is just kind of based on whatever number of samples we run this out to. And then what this is saying is that, in fact, for any T up until that point, so all along the trajectory, this risk curve is concentrating on this deterministic limit. And so here you can kind of see a picture of what this looks like. So in the very middle is a red line, and that's the theoretical curve that we get, which can be represented in terms of solution to a system of ODEs. And then around that, you'll see some bands that represent where the actual SGD curve is going to live based on dimension. And so when we take the dimension small, it's, sort of somewhere vaguely close to this theoretical curve, but as the dimension gets larger, it becomes closer and closer to that theoretical curve. And so what I want to emphasize here is that this convergence result is not about what SGD is going to do in the long time in terms of like where is the risk going to go eventually, but rather it's about converging to a specific trajectory for the kind of over the course of time. So this whole curve is what it's converging to. All right. So a couple of comments on this is that this type of convergence holds for other statistics as well, not just the risk, and I'll talk a little bit about that later. I'll go into some examples first so we can kind of see what this means, but then I'll also show you what these ODEs actually look like and how this theorem can be generalized to other types of statistics. All right, so we'll start with this simple example of binary logistic regression. And so here we're going to just have these two means for these two classes. And without loss of generality, we can assume that, we shift things such that one mean is just the negative of the other. So we have mu and we have minus mu. And then we're also going to take the two covariance matrices to be diagonal. Again, that's without loss of generality because I told you already that we're assuming that they commute. So I'm just fixing now what the basis is going to be. And then in this setting, this is the way that the risk equation will look. So here we're doing binary logistic regression for classification, and we're going to consider these two toy models. The first one is the simplest thing you can possibly think of, which is an identity model. So for both classes, K is just the identity. We're going to contrast this with the 0, 1 model. Here, all of the eigenvalues for both covariance matrices will be either 0 or 1, but in different locations. So in particular, we're going to partition the indices into these 4 groups. I00, I01, I10, and I11, corresponding to whether each of the 2 covariance matrices has either a 0 or a 1 in that entry. And we're going to also assume that each of these classes accounts for roughly 1/4 of the entries in D. Right, and so then the goal of this is a very simplified model, but the goal is that we want to use this 0, 1 to see the effect of non-isotropic data. So now we don't have just one eigenvalue, we have only 2, but still we can see some effect there, and also different covariances on the 2 classes. Okay, so we can look first at what happens with the risk, and already we see some differences between these 2 examples. So in the identity case, and I apologize for the labels being somewhat small, but here you can see that the risk goes down and then it sort of levels off, and it's leveling off at around 0.4. So it's in particular not going to 0. Whereas in the 0, 1 case, it does go down actually quite a bit further. So you can see that it seems like it's just continuing to go down towards 0, certainly below where the 1 for identity went. So this is going like below 0.1. And so the next thing that we might want to ask ourselves is, well, what direction are these 2 models learning? And I'll introduce, for the purpose of discussing this, 2 quantities. So M of t is going to represent the inner product of the mean with x, the SGD iterates. And then v is going to represent just the norm of the SGD iterates. And recall that mu is the class 1 mean. And so we might expect that if SGD is doing kind of what we want it to and it's learning something, then maybe x is going to align near mu. And so maybe we're expecting that m is going to get bigger. All right, so let's see what happens. Here I have what I'm calling the alignment with mu. And so this is m, but it's normalized by v. So we're normalizing it by the magnitude of that SGD iterate vector. And we see something interesting. So in the identity model, it was kind of what I was alluding to on the previous slide, that it's going up and then it's kind of stabilizing. So it's learning this direction of the mean. Something slightly different is happening in the 0, 1 case, that it seems like initially it's learning this direction of the mean, but then it's going back down again. And so this suggests that first it learns the mean, but now it's learning something different that somehow is better. And so a natural question to ask ourselves is, well, what direction is the 0, 1 model learning instead? So recall we've got this setup for the 0, 1 model, and we can think just sort of intuitively what directions should yield the best classification. And so one obvious thing that would improve classification is learning the direction of greatest distance between the 2 class means, which in this case is mu, because the class means were mu and minus mu. But something else that could be helpful would be to learn the direction of smallest variance, because then you're going to be more accurate. And so in this case, that's what I was calling the eigenspace of this I00. So that's where both of the covariance matrices have an eigenvalue of 0. And I'm going to now define a couple more things that will help us discuss this. So I'll say mu 0, 0, mu 0, 1, mu 1, 0, and mu 1, 1. These are going to denote the projections of mu in the direction of each of these eigenspaces. And mjk will be the alignment in the mu jk direction. And so what we're going to be interested in particular is m00, 0, which would be basically SGD aligning with the direction that it's in the direction of mu, but projected into the eigenspace where both covariance matrices have eigenvalue 0. Okay, so this should be like no variance and also somewhat in the direction of mu. And this actually ends up being what happens. So here is the graph that I showed you before, just showing what's happening with the alignment with mu. Now we break this down into the projections of mu into each of these eigenspaces. And what we see indeed is that the SGD is initially starting to align with kind of all of them, but then over time, it's aligning in particular with the 0, 0 direction, and less so with those other components of mu. All right, so we see this in the numerical simulations that I show, and maybe I should go back and just kind of briefly, in case it wasn't clear, say what these are. So in each of these curves, you see kind of a slightly squiggly line and then a narrower one inside of it. So the narrow one is the theoretical prediction based on numerically solving these ODEs, and then the other one is just SGD simulation. So you can see they match quite closely, and we can also see these results analytically. And that was one of the other reasons to look at the simplified model, is that this is one that's really tractable to look at analytically. So a couple things that we're able to show. First of all, that indeed, as the graphs suggested, the risk is decaying in the 0, 1 model towards 0, and it's decaying at a polynomial rate. We can contrast this with the identity model where the risk is bounded away from 0. And that's basically due to the fact that when all the eigenvalues are 1, you can't classify perfectly. When you have some eigenvalues that are 0, you really can't classify perfectly. So that's sort of the intuition there. The other thing that we see that distinguishes these two models is that the norm of SGD is actually growing at a logarithmic rate in the 0, 1 model, whereas it stays bounded in the identity model. We can also say something about these directions that I was discussing before, these eigenspace projections, in terms of the asymptotics of m sub ij. So m0, 0, remember this is the one that I was saying was the projection of mu into the 0, 0 eigenspace. And so this is the one that was growing in that graph, and it's growing at a logarithmic rate, so not terribly fast, but it is growing. Whereas the projections of mu in the other eigenspace directions, these ones are strictly smaller than the one that it's mainly running. The other thing that we can see is that when we normalize m by v, which is the norm of the SGD iterates, this is converging to 1/2, and we can show that exact value. Now, it is quite slow, but that is eventually what it converges to. All right, so now I wanted to go beyond this very simplified 0, 1 model to something slightly less simple, which is data with a power law spectrum. We're still looking here in the case where we just have two classes, the binary logistic regression. And what we saw in the 0, 1 model is that exhibits a trade-off between learning the direction of the mean versus learning the direction of smallest variance. And so a logical next question is, do we observe this when k has non-zero eigenvalues but still very small? So it's not realistic maybe that we would have eigenvalues that are really just 0 or 1. But perhaps we have, and in fact it happens often with real data, that a lot of the eigenvalues are kind of very, very close to 0. And so this we try and capture in this power law setup. And we see a transition, in fact, in the behavior. And we categorize this into two regimes, which we call the mild power law and the strong power law. And roughly, we'll see that the mild power law exhibits some similarities to the identity model, whereas this strong power law exhibits some similarities to the 0, 1 model. And so strong power law, basically, you want to think of that as like, really, there's a lot of eigenvalues accumulating very close to 0. So here is the more detailed setup. So lambda and mu are going to, lambda and u are going to be our eigenvalues and eigenvectors. We'll have the lambdas are having this this power law setup. So the index j over the dimension d, and then to some power alpha I, we could in principle take this to be a different alpha for the different covariance matrices. And then we'll also put a power law scaling on mu. So this, you can think of this is just like the entries of mu within this vector basis, and those are also going to have this power law with exponent b, or beta. And we're going to be particularly interested in the case where alpha is greater than 1. So if this is greater than 1, what that means is that, first of all, this matrix is going to have a limiting spectral density, and so it does really make sense to take this d to infinity limit. You see it approaching this this spectral density, and it's going to be supported on the interval from 0 to 1, which you can kind of see from the formula, and it's going to be unbounded near 0. So this is capturing the idea that I mentioned of we have eigenvalues really accumulating near 0. Okay? And we're going to further break this into two different regimes based on the size of alpha in relation to the size of beta. So the first one, which I'm calling the strong power law, this one we have alpha greater than beta plus 1. So we really have the alpha much bigger than beta. And what this is intuitively saying is that there exists some directions where the variance is small, but the mean is not, right? So this exponent is a lot bigger than this one. So the eigenvalues are really accumulating near 0 much more so than the components of mu. And intuitively, what we might see here is that learning the small lambda directions is going to be advantageous, right? We have some directions where the variance is going to be really, really small, but the mean is not so small. So these are good directions to learn. And that's kind of like what we were seeing in the 0-1 model. Then we contrast this with the mild power law case, where alpha is not so much bigger than beta. And in that case, the directions of small variance, they also have small mean. And so maybe it's not really so helpful to learn those. Okay, so I want to now show some graphs of what this looks like, and specifically comparing these two power law regimes with what we saw with the identity and the 0-1 models. And so as I kind of alluded to, the mild power law looks a bit more like the identity. In particular, when we look at the risk trajectory, we see that it's going down, but then it's leveling off at some value strictly above 0. Whereas when we have the strong power law, we see it continuing to go down further. It's not decaying quite as rapidly as the 0-1, but nevertheless it is still continuing to go down rather than leveling off. Okay. And we can also see a similar kind of picture in terms of the growth of m as what we were seeing in those other models. So recall that when we looked at the 0-1 in the identity model, in the 0-1 model, m was growing logarithmically, and the magnitude of the SGD iterate vector was also growing over time, whereas in the identity model, both of these things are bounded. And it's this distinction that actually motivates our threshold between the strong and mild power law. So here we saw a similar kind of distinction, that when you hit this value of alpha minus beta being greater than 1, the m begins to grow at a polylog rate, whereas when alpha minus beta is less than 1, the m remains bounded. And so this motivated us to look at that particular transition, and indeed we see that that also corresponds to a transition in the behavior of the risk function. We're still investigating whether there may be some other thresholds of interest. Indeed, we expect that there probably are. And one reason for that is by looking at this alignment with the eigenspaces. So here we thought about something kind of similar to what I was discussing with the 0-1 model, and just did sort of the simplest thing of, well, let's think about just projecting into the space associated with the top half of the eigenvalues versus the bottom half of the eigenvalues. And what we see is that in the mild power law case, m is aligning more so. So these are some normalized version of these projections. M is aligning more so with the upper half of the eigenvalues, whereas for the strong power law, m is aligning more with the lower half of the eigenvalues. But when we end, so I gave these two examples, which make it look very clean, but in fact, it's not quite so clean. If I kind of mess around with the alphas and the betas, you can get some examples where these two curves cross each other. And so this suggests to us that probably there's some other thresholds that might be interesting to look at beyond just this mild and strong power law dichotomy that I've presented here.